So refraction occurs because we get a wave bending as it reaches a boundary. And the reason it does this is because the wave will change speed. Most common diagram we see of this, we will have a boundary, we've got air, we've got some substance, transparent, we will shine some light into it, and it will bend towards our normal. So remember, our normal is a line that is 90 degrees to the surface, and on this we can draw two angles. We've got our angle of incidence, theta I, and this small one here will be theta r. What we can find experimentally is the ratio between sine of theta I, sine of theta r is constant, and we call that the refractive index of our substance. The refractive index of the substance is sine of the angle of incidence over sine of the angle of refraction. We said refraction takes place because we have changing speeds. What we also find is the ratio of these angles also is the ratio of the speed of light in those materials. So at this point we're looking at air, so the speed of light over the speed of light in the substance is equal to sine of the angle of incidence over sine of the angle of refraction. As we said, that equals the refractive index of our substance. We know when our light enters the material, its frequency is constant. So what that means, because we've got C over C in the substance and F is constant, we can also say that this will equal the wavelength over the wavelength in the substance. So for air, or when light's entering from air, we have these four relationships. So sine of angle incidence over sine of the angle of refraction equals the ratio of the speed of light equals the refractive index of the material equals the ratio of the wavelengths. If instead of air we have two materials, then we have a slightly different situation. So we can say sine theta 1 of sine theta 2 will equal the ratio of the speed of light in those two materials. If we then rearrange that, we can then say 1 over c1 sine theta 1 equals 1 over c2 sine theta 2. If we now multiply through by c, we can say that c over c1 sine theta 1 equals c over c2 sine theta 2. If we look back up to this equation here, c over the speed of light in that material is just equal to that material's refractive index. So this equation here will just simplify it down to n1 sine theta 1 equals n2 sine theta 2. And that fundamental equation is known as Snell's law. With refraction, the key thing we're always looking at is ratios. So there's four relationships that we have. So we have ratio of the refractive indexes, we have ratio of the sine of the angles, we've got ratio of the wave speed in each material, and we have the ratio of the wavelength in the material. So these four are our refraction ratios. The key thing to remember with these is the refractive index ratio is the opposite way around to the others. So in these examples, the sine of the angle, speed of the wave, and the wavelength, we've got material 2 over material 1. Which means for refractive index, it must be material 1 over material 2. So this is the odd one out because its ratio is the opposite way around to the other three.